Okay, have a good day, students. Today we are going to see about the carrier concentration in p-type semiconductor. So already we have seen about the n-type semiconductor. So here, let me tell you about the energy band diagram for p-type semiconductor. So as you know, the dopant here used is a trivalent impurity. So because of the trivalent impurity, so if you consider the pure form of semiconductor, like silica or germanium. So it consists of 4 electrons in the outermost orbit. So if you think that the dopant is added, for example, boron is added here, and the other places you have silica. So you know that for boron, it has only 3 electrons in the outermost orbit. So 1, 2, 3. So here it is vacant, so there is a hole. So the number of holes will be more when you add this boron into the silica. Okay, so more number of holes will be there by the addition of boron into it. Here, in the previous case for n-type semiconductor, when you add a dopant, that is pentavalent dopant, phosphorus, so there a lot of electrons is donated to the host atom. Here boron is added, so holes is present there. Okay, so this holes, what will happen? So here it is donated, the electron is donated, so it is called as donor, and these holes, they will accept an electron from the host atom. Okay, so the holes will accept an electron from the host atom, so hence it is called as acceptor. So here, look at this diagram, that is energy band diagram. At the bottom you have the valence band energy. It consists of the electrons at first, and above this valence band you have a this is an acceptor energy level, so EA. Okay, so this acceptor energy level, it consists of the holes. This is generated because of the holes due to the dopant. Okay, so plenty of holes will present at the acceptor energy level. Now when you give some energy to this material, that is semiconducting material, at first the valence band electron move towards the conduction band energy. So here you can see 2 electrons are moved to the acceptor energy level. Therefore 2 electrons created in the 2 holes created in the valence band. So the number of electrons in the acceptor energy level, that is equal to the number of holes in the valence band. Okay, so number of holes in valence band, so that is equal to number of electrons in acceptor energy level. So that is nothing but the EA. Okay, so this is the concept at first. Now we have to derive the density of holes in the valence band as well as the density of electrons in the acceptor energy level. So let us do one by one. So at first, density of holes in the valence band. So you know already about this density of holes in the valence band from the intrinsic semiconductor. So already we have derived this in the intrinsic carrier concentration. Okay, so there we have derived the density of electrons in the conduction band as well as density of holes in the valence band. So here this density of holes in the valence band is given by P is equal to 2 into 2 pi m h star, since it is hole. This mh star is the effective mass of hole. 2 pi mh star kt by h square power 3 by 2 exponential of EV minus EF by kt. Okay, EV minus EF by kt. So this can be taken as equation number 1. So what is the second case? We want to find for the number of electrons in the acceptor energy level. Okay, so that can be given as so it is otherwise called as ionized acceptors. So we can write it as density of ionized acceptors. Ionized acceptors, since they are acquiring an electron, so it is called as ionized acceptor, or you can say it as density of electrons in acceptor energy level. So you can say it as EA. So it is given by, that is equal to NA into F of EA. NA into F of EA. So NA is the total number of carriers present in the its acceptor energy level, and F of EA is the probability of finding the electron in acceptor energy level. Okay, so NA into, so F of EA is given by NA into, you know, the probability distribution function F of E. So F of EA is given by 1 by 1 plus e power EA minus EF by KT. NA into 1 by 1 plus EA minus EF by KT. So this is equation number 2. So we got two equations. So here you see EA minus EF. EA is in the higher energy level. EA is in the higher energy level, and EF is in between this valence band and the acceptor energy level. Okay, so this Fermi energy is lower energy and acceptor energy level is higher energy level. So EA minus EF, that is a positive value. Exponential of this value is a positive value. Now what happen means, when it is a positive value, the exponential of this value also become very much greater. So EA minus EF is greater, or greater, not greater, you can write it as positive value. It's a positive value. Therefore exponential of EA minus EF by KT is a greater value. So since it is greater, the value should be very much greater than 1. Okay, so you can write, instead of writing 1 plus e power EA minus EF by KT, you can write it as, just neglect this 1 and write the remaining thing. So the density of ionized donor, density of ionized acceptor, ionized acceptor is equal to NA into NA into 1 by e power EA minus EF by KT. Okay, so we got this value. So now again you can rearrange this. So that is equal to NA into exponential of minus EA minus EF by KT. Okay, so that is taken to the numerator, so there is a negative sign that is existed here. So you can change this as this becomes minus and EF that becomes plus. So the density of ionized acceptor is equal to NA into exponential of EF minus EA by KT. So put this as equation number 3. So we have equated these two. Since the number of electrons and number of holes both are same, so we are equating these two. So equation 1 is equal to equation 3. So at equilibrium, the number of electrons in the valence band, number of holes in the valence band is equal to the density of acceptors. So equation 1 is equal to equation 3. So you can write first the equation 1. So 2 into 2 pi m h star 3 m h star kt by h square power 3 by 2 into exponential of EF minus EV minus EF by KT, so which is equal to NA into exponential of EF minus EA by KT. So now let us solve this. So put this as equation number 4. So by solving this, you have to find the value for the Fermi energy. So as in the previous case, we have to solve this. So take the exponential terms in one side and the remaining term on the other side. So here you see exponential of EV minus EF, and so while you take this to the left hand side, you will get EV minus EF, so minus EF plus EA by KT. Okay, so that is equal to NA divided by 2 into 2 pi m h star KT by h square, so power 3 by 2. Now let us see. So here EV, then minus EF minus EF. So EV plus EA minus 2 EF divided by KT. So just write next. So exponential of EV plus EA minus 2 EF by KT by KT is equal to NA divided by 2 into 2 pi m h star KT by h square power 3 by 2. Okay. Now we can take that log on both sides to remove this exponential. So taking log on both sides. taking log on both sides. So while taking log, log of exponential, it becomes, it will be cancelled. So you will get EV plus EA minus 2EF by KT. So that is equal to log of NA divided by 2 into 2 pi. So as it is, you can write KT by H square. This is K, that is power 3 by 2. So what is the next point? So here we can take EV plus EA minus 2EF is equal to KT log NA divided by, so 2 into 2 pi MH star KT by H square power 3 by 2. So let us move to the next system. So what you want is to find the EF, that is the Fermi energy. Okay, so here we have EV plus EA on the left hand side. So while you take that to the right hand side, it becomes minus. This is plus. So here already one minus is there. So when you take this as positive 2EF, so multiply by minus in the right hand side. So you will get 2EF is equal to EV plus EA minus KT log NA divided by 2 into 2 pi MH star KT by H square power 3 by 2. And finally EF is equal to EV plus EA by 2 divided by 2 minus KT by 2 log NA by, so 2 into 2 pi MH star KT by H square power 3 by 2. So the equation number is, I think it's 5. Equation number 5. So EF value, we found the value for Fermi energy for the p-type semiconductor. So here in this case, at 0 Kelvin, this value becomes 0. Since this temperature value is 0, as a whole that value is become 0. So EF is equal to EV plus EA by 2. That means the Fermi energy that is situated in between the valence band and acceptor energy level. So here you can see this is the Fermi energy that is in between EA and EF. So from this equation we understood that. Okay, so that is at 0 Kelvin it is in between. When the temperature increases, the Fermi energy level slowly shifted upwards. Okay, so this is equation number 5. So we got the Fermi energy. Now let us substitute this equation 5 in equation 1. So equation 1, substitute equation 5 in equation 1. So what is equation 1? P is equal to 2 into 2 pi m h star kt by h square power 3 by 2 into exponential of, so here only we have to substitute exponential of EV minus EF, exponential of EV minus for EF you have to substitute the equation 5. For EF, EV plus EA by 2 minus EV minus EF. So that is minus KT by 2 log NA divided by 2 into 2 pi mh star KT by h square power 3 by 2. Close this. So we have substituted now. Now we have to simplify this. Okay. So in the next step, I think without writing this column, this bracket itself, we can write minus. So here it becomes plus. So we can write straight away, go to the next step here. So P is equal to, this term will be exist as it is, 2 pi mh star kt by h square power 3 by 2 exponential of, so here by taking the LCM you will get 2 EV minus EA minus, so here it is EV minus okay, so EV minus EA by 2 plus the remaining term KT by 2 log NA by 2 into 2 pi mh star KT by h square power 3 by 2. Okay. Now 2 EV minus EV, so it becomes EV minus EA. So P is equal to 2 into 2 pi mh star KT by h square. So this is h. So h square by power 3 by 2. So exponential of EV minus EA by 2 plus the remaining term KT by 2 log NA by 2 into okay, so here I missed one thing. So EV minus EF by KT. So So that also included here 2 kT. So here it becomes kT and kT, so that will be cancelled, and here it is just 1 by 2. 1 by 2 log Na into 2 pi m h star kT by h square power 3 by 2. Okay, now let us solve this. 2 into 2 pi m h star kT by h square exponential of, so you can write this as e power a plus e power n. So it is as exponential of, so you can write e power ev minus ea by 2 kT into half log this value. Okay, so exponential of half log this value. So first you can write as, okay, so before doing this, one more step. So exponential of this plus, so this is n log m form, so you can write log Na power 1 by 2 divided by 2 power 1 by 2 2 pi m h star kT by h square power, here it is 3 by 2, so 3 by 2 the whole power 1 by 2, that is 3 by 4. Okay, so the next step we can split this. So by splitting that, P is equal to 2 into 2 pi m h star kT by h square power 3 by 2. So you can write e power ev minus ea by 2 kT. So exponential of this log. Okay, so that will becomes into Na power 1 by 2 divided by 2 power 1 by 2 and 2 pi m h star kT by h square power 3 by 4. So here we can almost we reached the first final expression. So this is 2 power 1 by 2, which means root 2. So these 2 can be written as root 2 into root 2. So 2 power 1 by 2 into 2 power 1 by 2. So one of them is cancelled, and this is common term, and this is also common term. Base is common, so power is different, 3 by 2 minus 3 by 4. So again you will get 3 by 4. Okay, so in the final expression you can write it as, so here 2 into 1 power 1 by 2, so Na power 1 by 2. So you can write 2 Na power 1 by 2. So this value 2 pi m h star kT by h square, the whole power 3 by 2 minus 3 by 4. So that is again becomes 3 by 4. E power ev minus ea by 2 kT. So this is P. So ea is the highest value and ev is the smallest value. So this ea minus ev is an energy difference that is given by delta E. So since it is opposite, ev minus ea, it becomes minus delta E. So we will get P is equal to 2 Na power 1 by 2 into 2 pi mh star kT by h square power 3 by 2 exponential of minus delta E by 2 kT. So this is the final expression. This is the final expression for the density of charge carrier in the case of p-type semiconductor. Okay, so regarding the variation of Fermi energy level with respect to the temperature and doping concentration, so that we will see in the next video. So thank you, students.